All right. So thank you, everyone. The name of our paper is Enhancing Metabolic Syndrome Prediction with Hybrid Data Balancing and Counterfactuals. And we are from Embedded Machine Intelligence Lab of College of Health Solutions, Arizona State University. So now let's at first introduce ourselves to metabolic syndrome. So metabolic syndrome is basically an indicator of a cluster of risk factors. For example, obesity, then dyslipidemia, hypertension, insulin resistance, many risk factors combined together is considered metabolic syndrome. And globally, more than 25% of adults suffer from this condition. It significantly increases cardiovascular diseases and type 2 diabetes risk. And there are existing solutions for detecting metabolic syndrome, but there are also challenges. For example, class imbalance in the data sets, then data scarcity and missing values, and then methodological inconsistencies, and also limited interpretability of clinical use. So class imbalance is one of those major challenges. And here are some of the strategies to overcome that challenge. For example, the trivial solution is to just train your model on imbalanced data set without any oversampling. And in that case, your model can be biased towards the majority class, so which is not a good solution. The second strategy can be using random oversampling only on the training set. In that case, some of the samples from the training set will be repeated, and in that case, the test accuracy will be better than the first approach, but still we can do better. Another approach can be balancing the data with help of synthetic data, and we have established methods for that, for example, SMOTE or ADASYN. And even though they were proposed long time ago, they are still very popularly used. There are also recent methods based on generative models, for example, BEAD-C2 or AMEN. Now, our question is, can we improve the performance of our machine learning models with a hybrid data balancing method? And can we also enhance the interpretability of metabolic syndrome prediction with counterfactual analysis? So this is our proposed solution, MetaBoost system. So here, what we do, at first, we start with a challenging data set, which suffers from class imbalance. And then we use a hybrid data balancing method, combining CTGAN, ADASYN, and SMOTE. And then we get a balanced data set. After that, we train our models for metabolic syndrome detection, and we get the predictions on the test set. And finally, with counterfactual explanation, we identify which features are important to remove or prevent metabolic syndrome. So to evaluate our system, we use this data set. This data set was published by the organization NHANES. And in this data set, we have 2,401 individuals with 13 clinical features. Those features are age, sex, waist circumference, BMI, blood glucose, HDL, triglycerides, etc. And the target class is metabolic syndrome, either the presence or absence of metabolic syndrome. So we at first pre-processed the dataset by removing one of the features, which was marital status, and we removed it because it had a high number of missing values. And then we encoded the categorical features, for example, sex and race. And we also used mean imputation for filling out the missing values for income, waist circumference, and BMI. And finally, we split the train and test sets. we kept the test set balanced, and on the train set, we used our MetaBoost method. So these are the machine learning methods that we used. So we have the XGBoost classifier, then random forest, then TabNet, regression, then multi-layer perceptron, and finally decision tree. And these are the evaluation metrics that we used: accuracy, precision, recall, and F1 score. And these are the results we got. So at first, we just established our baselines. One baseline would be to train without any data balancing. And in that way, the best F1 score we got was 0.824. Then another baseline was when we performed random oversampling on the training set. And in that case, the best F1 score was 0.849. And in our MetaBoost method, what we do is basically we use different combinations of data balancing methods with different weights that represents what percentage of the samples in a batch would come from which data balancer. For example, if the weight is 0.4 and 0.6 for this combination, ADASYN and CTGAN, in that case, that will mean that out of all the data sets, all the data points generated to balance the data, 40% of them will come from ADASYN and 60% of them would come from CTGAN. In this case, for example, we use all three of them, SMOTE, CTGAN, and ADASYN. In this case, 5% of the examples are coming from SMOTE, 55% are coming from CTGAN, and 40% are coming from ADASYN. That way, we create a hybrid set of data points to balance the data. And we see that our MetaBoost method, when we use ADASYN and CTGAN with these specific weights, we get an accuracy of 0.871 and we get an F1 score of 0.868, which is higher than the previous baselines. It is also higher than these baselines where we use only SMOTE or only ADASYN or only CTGAN, which are used in many different research papers. So we see here that our MetaBoost method can achieve an accuracy improvement of up to 1.87% over the baselines. And here we also plot the accuracy changes with different weights. For example, here the blue curve is representing the different accuracies we found for the ADASYN plus CTGAN combination. The orange one is for SMOTE plus CTGAN combination, and the black one is for SMOTE plus ADASYN combinations. And as consistent with the table, we found that the highest accuracy was found with the ADASYN plus CTGAN combination for a weight of 0.4 and 0.6. So in summary, the MetaBoost method is a weighted combination of synthetic data from multiple methods. And we varied the weights with an increment of 0.05. So for two cases, for two data balancer cases, we had 20 different weight combinations. If the weight of the first data balancer is 0.05, in that case, automatically for the second data balancer, it would be 0.95. And as we increase the first one, we decrease the weight of the second one. And that way we have 20 different combinations. For three method combinations, we have 235 different weight combinations. There we will have three different weights for three different data balancer, for example, 0.05, 0.05, and the third one will be 0.90. So we will keep it fixed here, and then we'll vary these two. Then we will change it to 10, and then again we'll vary these two. That's how we got 235 different weight combinations. And finally, our counterfactual analysis will provide us with the information about which features are responsible for metabolic syndrome and how could we prevent the metabolic syndrome. So we used the nearest instance counterfactual explanations method, which basically finds the nearest unlike neighbor and then create a counterfactual example which is close to the decision boundary, so that the distance from the original data point to the counterfactual point is not too high, and also so that a lot of features are not needed to change to get to the counterfactual data point. So these are the properties of our counterfactual examples. So on average, the normalized distance from the original data point to the counterfactual data point is around 1.489. And average sparsity is 2.054. So the average sparsity of 2.054 indicates that on average, around 2 features would need to be switched or changed to get to the counterfactual example, or to flip the class prediction from metabolic syndrome, from presence of metabolic syndrome to absence of metabolic syndrome, and which translates to around 17% of the available features. And here we present which features are more critical than others. For example, we see here that the blood glucose is the most critical feature for metabolic syndrome. If we can regulate blood glucose, in that case, we can prevent metabolic syndrome. For example, here we can see that 50% of the cases, in 50% of the cases, blood glucose was one of the features that would need to be changed to reach to the counterfactual point, or from presence of metabolic syndrome to absence of metabolic syndrome. Then the second most important feature was triglyceride. In 46.7% of the cases, our MetaBoost method will suggest that, okay, you will need to change the triglyceride, reading of triglyceride. We found that sex and race had minimal effect on the counterfactual explanations. So metabolic syndrome in general does not depend on the sex or the race of the person. It's mostly on the biomarkers. And here are some visualizations of the counterfactual explanations. And these decision boundaries were generated with a random forest classifier. So I'm happy to explain it after the presentation if there's any questions. So to summarize, this is our contribution, the MetaBoost framework, which is a hybrid data balancing approach, which gets a 1.87% accuracy improvement over individual methods. And we also achieve 0.868 F1 score on prediction of metabolic syndrome. And finally, we provide clinical interpretability through counterfactual analysis. So this work has vast clinical significance because it addresses the critical healthcare challenges, which is class imbalance and data scarcity. And it also provides interpretable machine learning models, and that can facilitate the design of interventions to prevent metabolic syndrome. So that was all. So let us know if you have any questions or any feedback. Thank you so much.